today I will present an overview of the SuperCDMS SNOLAB experiment. Let me first start with a short overview of the SuperCDMS Collaboration. So the collaboration has about 150 members from 26 institutions with a strong contribution from the US and from Canada, but we also have collaborators in Europe and from India. So SuperCDMS is a direct detection experiment, and we already had a very nice introduction talk to as the first talk today. So let me just briefly summarize the concept of direct detection and how we can do so with cryogenic detectors. So the dark matter interactions fall into two categories. So we first have the nuclear recoils. So these are the traditional WIMP channel signals, but they are also mimicked by neutron and neutrino backgrounds. And we have electron recoils, which means that the incoming particle interacts with an atomic electron, which is true for most of the background sources, and also for light dark matter interactions, and for more exotic interactions like dark photon absorption or the absorption of accident-like particles. And in the detector, such dark matter interactions then show up depending on your detection approach, where you could search for scintillation light, for heat of phonons, or for charge. And SuperCDMS is an experiment that makes use of both phonons and charge with cryogenic detectors, where we have two different approaches. We have detectors we call the HV detectors, where we have a phonon-only readout, and we have the so-called ISAP detectors. I'll explain what this means in a minute, where we both collect phonon and charge signals and have the ability to also discriminate electronic and nuclear recoils, so have a very nice background discrimination. So on this slide, we see the physics reach for SuperCDMS SNOLAB with respect to the potential dark matter mass candidates. So for very low masses, we would have sensitivity to dark matter by absorption channels like dark photon and accident-like particles. And for a medium mass range from about 0.5 MeV to 10 GeV, we will have sensitivity through electron recoil interactions. And for the traditional WIMP channel, our focus is on the nuclear recoils with a mass range between 1 to 10 GeV. The difference here for different detectors is that for the ISAP detectors, we have a very nice discrimination between background-like ER signals, or the electron recoils, and the signal-like potential dark matter interactions, which will then be falling into this nuclear recoil category. Okay, so I will speak a bit more about the SuperCDMS SNOLAB project. So SNOLAB is one of the deepest underground facilities with a very nice overburden of 2 kilometers of rock, which is equivalent to 6,000 meters of water. This reduces the cosmic muon flux by 50 million. And here in this facility, we are currently building our SuperCDMS SNOLAB experiment. So this is how the experiment will look like. So we have our dilution refrigerator, which is the heart of the experiment, with a closed loop cryogenic system, which is under commissioning right now. And the experiment is also supported by the so-called CUTE facility. So CUTE stands for Cryogenic Underground Test Facility. And this is used for fast turnaround detector and equipment testing for SuperCDMS. But it's also its own facility in the sense that CUTE will then have its own R&D and research program when we are finished with commissioning the SuperCDMS experiment. So we will expect some early science results with SuperCDMS detectors operated in the CUTE facility. So the SuperCDMS SNOLAB consists of our the so-called snow box, where we operate our detectors. You can again see the dilution refrigerator, which has the ability to bring us to a base temperature of 50 millikelvin to operate our detectors. The initial plan for SNOLAB, for SuperCDMS SNOLAB, is to operate with an initial payload of 4 so-called detector stacks or towers, whereas each tower consists of 6 detectors. So in total, we will have 24 detectors with a total mass of something like 30 kilogram. The whole experiment, including its shielding, is placed on a seismic platform, so to get rid of vibrational noise, and also the complete cryogenic system is designed in a way that we avoid vibrations where possible. For example, we also hang copper cans that are enclosing our detectors or towers by hanging them on Kevlar ropes. For the backgrounds, we aim for being dominated in the nuclear recoil channel by solar neutrinos when reaching our full potential and the full exposure. So here are some pictures of the current status. So this is the seismic platform that has been commissioned this summer, and this is a picture from about 2 weeks ago. This is the innermost part of the fridge, which is currently tested at that Fermilab. We have commissioned the radon, the low radon clean room at the SNOLAB facility already. And here you can see a picture of the assembled lead shield by the manufacturer. And there's also a time-lapse video of the assembly. So here you can see that this consists of polyethylene in the middle, surrounded by lead, about 100 tons of lead. And here you see the feed-throughs on the front and the back for the pipes going to the electronic system and the cryogenic system. So the shield is now completed and is ready to be shipped and will be installed early next year. Okay, now talking a little bit more about the SuperCDMS detector technology. So we're using, as I mentioned before, 2 different types of detectors, the HV detectors and the ISIP detectors. The HV detectors have the advantage of the high voltage detectors is that we have here a very low threshold, which benefits from the NTL effect that was introduced earlier today. Meaning that we not only measure the primary recoil, but we also measure secondary phonons created by applying a high voltage that drifts the charges across the crystal. And the other detector type we have is the ISIP detector. This has the advantage of providing a low background, because here we have a prompt phonon signal and an ionization signal, and the ratio of both can then be used to discriminate between nuclear and electronic recoils. Here are some pictures. So on the top we have the HV detector, on the bottom we have the ISIP detectors. Here we see that the channel map is a little bit different. So here we have 3 channels as a circle. Here we have 4 channels of the circle. So this is then the mask that optimizes the detector performance for the different approaches where we benefit from those detectors. And not only do we have 2 different detector configurations, but we also have 2 different substrates we are making use of, so germanium and silicon, because this complementary provides us with sensitivity to lower dark matter masses for the silicon detectors and to lower dark matter cross sections for the germanium detectors. So here we have an overview about the low threshold versus the low background mode. So for the low threshold modes, we have the disadvantage that we then lose the ability to discriminate between nuclear and electronic recoils, but due to the amplification, we still have the ability
you have 2 minutes left.
Yeah, okay, thanks. You have the ability to boost your signal to background ratio, and you can very easily reach thresholds below 1 kV, or if you go to energy electron equivalent to something like 4 eV, as demonstrated in this paper with CDMS light. And for the ISIP detectors, as I mentioned before, you can nicely discriminate between background-like sources, like here for barium calibration, which is limited to the electronic recoil band, and against nuclear recoils here in gray, which is then our search window for WIMP interactions. And just as a summary, so this is the projected SuperCDMS sensitivity. There you see the different sensitivities for different detector types, silicon HV going to lower WIMP masses, whereas germanium goes to lower cross sections. And in order to make it possible to compare different experiments against what SuperCDMS is aiming for, there's a public dark matter limit plotter. Here's the link to it. So this has been updated quite recently and contains limits from all the experiments on the world. And users are encouraged to submit their data if you want to be included into this public limit plotter. So here's the conclusion. SuperCDMS SNOLAB will begin its installation next spring, summer, and we expect core detectors by fall 2023. And we are also having a rich R&D program establishing a new detector type, the so-called HPEV detector, which will reach very low thresholds and then also be able to search for very low mass dark matter candidates. With that, I thank you for your attention.